So to summarize again the whole chapter, the ideas, these equations on this page are the equations that are always correct. The force, the Lorentz force, is QE plus QV cross B. This is always correct. Integration of E dot ds is minus d by dt of the magnetic flux for a fixed contour. This is the case for a fixed contour only, and you can bring the derivative into the integration on the magnetic field only if this is if the contour is fixed. This is a subtle issue, so you have to kind of take it as a given. If you want, again, there are more advanced notes I have that explain this in detail. So if you have a fixed contour, integration of E dot ds is minus integration partial b by partial t dot dA. We're not going to use this form, this blue form in the course. We always use this form, but you just need to make sure you understand that the integration of E dot ds is not equal to minus d phi by dt always. It's only equal to minus d phi by dt when the contour is fixed. The contour that you're integrating over is fixed, it doesn't move, change with time. And also the definition of the EMF, that it's integration of the force per unit charge dotted into ds going around the closed loop, that's the definition of the EMF. These are the equations that are always correct. The one in blue, the Lorentz force, and the EMF definition. And you can also prove that the EMF with this basic definition is always equal to minus d phi by dt. And we discussed this a bit before. It doesn't matter if the wire is moving and the magnetic field is constant in time, or the magnetic field is changing with time and the wire is fixed, or both are happening at the same time. The wire is moving and the magnetic field is changing with time. It doesn't matter. Always the EMF is equal to minus d phi by dt. So the nice thing then about solving any problem in this chapter, it doesn't matter the reason why the magnetic flux is changing. To get the EMF for any problem, you just get the magnetic flux, see how it changes with time, multiply by the number of loops, and that'll give you the EMF. If you want to get the direction of the induced current, you can use Lenz's law. And as we showed, Lenz's law works if you have fixed wires and the magnetic field is changing with time, and it also works if the wires are moving and the magnetic field is constant in time. So you can use Lenz's law with the same method in all cases. Now, if you get a very specific situation when the contour is fixed that you're integrating over, then in that case, the EMF becomes integration of E dot ds. Remember, the EMF is not always equal to integration of E dot ds. It becomes equal to integration of E dot ds if the wires are fixed. And when the wires are fixed, integration of E dot ds is minus d phi by dt. And you can combine these two then to get the relationship that gives a nice way to relate the electric field to the EMF to the rate of change of magnetic flux. So the EMF is integration of E dot ds, and it's equal to minus d phi by dt. And this equation holds that the EMF is equal to the integration of E dot ds. This equation holds only when the case where you have fixed wires. And so if you get a problem where you want to calculate the electric field going around some closed contour, this is the equation to use. Integration of E dot ds is minus d phi by dt.